Hello everyone, my name is Alejandro, and this is the PhD project that I've done these 3.5 years, which concerns data-driven query by Vocal Percussion, which is about transcribing and retrieving vocal percussion sounds from databases. First, I will walk you through the topic itself and the two subtasks that it has, and we talk about the data as well. We will talk about online vocal percussion transcription and offline vocal percussion transcription, meaning online in a real-time regime. And then we will dive a bit into drum sample retrieval by vocal imitation, and then we will share some perspectives about the outcomes of the project and future paths, future directions. So first, talk about the two tasks, which are vocal percussion transcription and drum sample retrieval by vocalization. Vocal percussion transcription concerns with the transcribing of a stream of vocal percussion sounds or an audio file of vocal percussion sounds, whereas drum sample retrieval by vocal imitation is about retrieving similar sounding samples by vocalization from a dataset of drum samples. If we want to retrieve, for instance, a similar sounding kick drum to what we have in our head, then we will imitate it vocally and the algorithm will retrieve such sample. So speaking about the data now, we have two different types of vocal percussion sounds. The first ones concern beatbox sounds, which are mostly percussive phonemes. They display quite good consistency in articulation, and also they are monophonic, but sometimes they are polyphonic, pronouncing a snare drum and a kick drum in the same phoneme, in the same sound, which are some signs of skilled beatboxers. In contrast, amateur vocal percussion, they use percussive and vowel phonemes, sometimes at the end of the syllable. And also there is some inconsistency in articulation, which affects the performance of transcription algorithms, and also they are monophonic. They performance don't usually imitate kick drum or a snare drum at the same time. They do it separately in the whole audio file. The problem we found in the very beginning of the project is that for Beatbox, we have a quite extensive database of sounds, 3,000 sounds around that. And in amateur vocal percussion, we only have 800 sounds from an earlier database that was recorded. So we have to tackle this topic, this issue, in the beginning, because we only have 800 sounds, and for data-driven, to apply neural networks to these very few sounds, then it's not enough, because it will overfit. Basically, the algorithm will not be as statistically reliable as if we had more data. So we had to record more data for this. And this is how we recorded the amateur vocal percussion dataset, which gathered 28 participants, almost 5,000 vocal percussion sounds. It had onset and label annotations with 4 drums, a kick drum, snare drum, close hi-hat, and open hi-hat. Those are the label annotations, and it's only amateur vocal percussion, so no beatboxers participated in the recording of the dataset. And this dataset, of course, is publicly available in Zenodo. All right, let's dive now into online vocal percussion transcription, which is real-time vocal percussion transcription. Usually the transcription workflow works this way. We start from an audio file, And this audio file has different sounds, different vocal percussion sounds along the file. And we identify the moment where each of these sounds begin. So this is the onset of the sounds. We perform onset detection. And we assume that the sounds themselves, they are in between these moments, in between these onsets. So we take what's in between all these onsets and we label them. So this is called classification. We say, well, in between this and this onset, there is a kick drum, or there is a snare drum, or a hi-hat, close hi-hat, open hi-hat, whatever the taxonomy is. Online, so in real time, this process is constrained to the very beginning of its sounds. So we have to do it at the same time as the participant or as the user vocalizes the sound. We have to get the transcription. We have to already know if this is a kick drum, this is a snare drum, etc. So it has to be done very quickly. So this is the challenge of online transcription. It's the real-time triggering of drum samples, or it could be it's usually a triggering of drum samples, but it could be whatever the result of the transcription, and via vocal percussion. And usually the less delay between the vocalization of the sound and the response from the system, usually the less delay, the more perceptually pleasing will be for the user. And usually it would be better to not exceed the 50 millisecond mark in delay based on previous experience, previous experiments in this front. For onset detection, we usually use causal models, which these are models that use only information from the past, not from the future of the audio file, and with high time resolution, so very precise in time. Also in classification, we usually get single frames classifier with different window lengths and offsets. So we place different windows of different lengths around the buffer, around the region that we are allowed to analyze in this very, very short amount of time. And these algorithms, both for onset detection and classification, have low computational complexity, so to avoid extra delays. So for onset detection, we tried different heuristic methods based on handcrafted features, engineered features like the high frequency content, the complex method, the phase of the spectrogram, etc. Then we use a state-of-the-art pre-trained recurrent neural network, which was trained for musical pieces. And also we trained around recurrent neural networks ourselves, which are 6 of them. So in the end, we have 8 results. And the results are given here. Usually we see that recurrent neural networks give the highest accuracies if one scores is a measure of accuracy in this kind of task. We have the lowest time deviations from ground truth onsets in general. And also the superflux, which is a description, it was the best descriptor to achieve heuristic onset detection. And this is because the superflux is based on the spectral flux descriptor, but it also has vibrato suppression. So we hypothesize that this vibrato suppression would discard false positives or false onsets. And then the accuracies seem to be not high enough also for this onset detection, for this real-time onset detection, which are usually around 90%. So there will be 10% of the onsets that will not be detected. So we wonder if this would constitute a bottleneck in transcription performance, which we will see the following time. Usually we see that the delay of 20 milliseconds, it's quite below our reference 50 milliseconds, and we see that usually accuracies do not get that much better from this delay on. So we think it will be a nice delay to achieve onset detection. And with respect to transcription, to classification, there is a problem here. And it's not on the front of Beatbox, but in the front of vocal percussion, amateur vocal percussion. This is that, for example, if I wanted to imitate the snare drum and the close hi-hat as ta and ti, respectively, these two syllables have the same beginning. The beginning is the T phoneme. So in real time, algorithms would only have access to the very beginning of the syllables, and because they are shared between ta and ti, then the algorithm would get confused because it's the same beginning for both syllables. So to avoid this, we tried to find which would be the best phonemes to perform amateur online vocal percussion transcription with. And we based our decision in 3 criteria. This is the frequency of use, which are the most popular phonemes in vocal percussion transcription datasets. Also the spectral similarity to the drum sounds of each phoneme, and also the classification separability, like how separable are these phonemes in a classification task. With respect to the frequency of use, we found that the phoneme P, K, T, Ts, and Ch, these are the most used phonemes among participants. So we got these phonemes and we analyzed the spectral content and also compare this content with that of different drum sounds. So we see that for the kick and snare, the phoneme P and the phoneme K are the most similar, whereas for close hi-hat and open hi-hat, the phonemes T, Ts, and Ch, they are they have similar spectral shapes. So those could be good candidates to represent kick drum, snare drum, close hi-hat, and open hi-hat by themselves. Also, attending at classification separability, we can see that the P and the K phonemes are highly separable from each other and also from the rest of the T-based phonemes. But the T-based phonemes, the T, Ts, and Ch, they are not as highly separable among each other. So this is we get these results from the confusion matrix and applying different machine learning algorithms and doing an average of these results. So the final phonemes in this respect would be for amateur vocal percussion transcription in an online regime would be P for kick drum, K for snare drum, T for close hi-hat, Ts for semi-open hi-hat or open hi-hat sometimes, and Ch for open hi-hat, or if some transcription demands the inclusion of more instruments like crash cymbals or rides, then it will be used for this as well. So now that we have the phonemes, let's get to the real-time online classification of this. So for an online classification, the region there that we are working with will be divided. We will place in the region different frames. So a total of 10 frames of different lengths, 23 milliseconds and 46 milliseconds will be placed along the buffer somehow. And we will measure the classification power of these frames. So, and we will try different algorithms for this. Concretely, we tried some heuristic algorithms made using heuristic features and K-nearest neighbors algorithms, and then a multi-layer perceptron algorithm and a one-dimensional convolutional neural network. And we see that the one-dimensional convolutional neural networks consistently give the highest accuracy, but both for amateur vocal percussion and for beatbox. We see that the selected phonemes are highly separable. So this is a good choice of phonemes, and it usually reaches 95% accuracy. So basically, and we arrive also that we see that the 20 milliseconds mark of delay, it's usually also a good mark for, as we saw in onset detection. So if both onset detection and classification can recognize sounds in 20 milliseconds, this is a good sign, because the delay is not as high, and users wouldn't be that dissatisfied with the result of the online transcription. And finally, beatbox sounds are not as highly separable online, sometimes reaching 80% accuracies, but at high delays. All right, so now let's talk about offline vocal percussion transcription. So in this case, we have access to the whole audio file, and in consequence to the whole region in between each onset. So we have more information to model. We tried different algorithms for this, some heuristic, like the online case. We tried a convolutional neural network, a recurrent neural network, and a convolutional recurrent neural network. We measured performances in accuracy scores, like the F1 score, also the relative and the absolute deviation from the onset times, so the predicted onset times and the ground truth, and also the inference time, so how long did each algorithm take to arrive at the prediction of the onset. We measure the error as well using the standard deviation and the 95% confidence interval, which is derived from this standard deviation from several iterations of each of these experiments. In general, we find that convolutional neural networks, convolutional recurrent neural networks, give the maximum accuracy scores, and also the minimum time deviations from ground truth onsets. But these accuracies and deviations are quite comparable with those from RNNs, from recurrent neural networks. And RNNs, they have a significantly shorter inference times. In particular, they are 9 times or around 9 times as fast as convolutional recurrent neural networks. So if they have comparable performances, then usually we advise for people implementing these onset detection algorithms to implement recurrent neural networks instead of convolutional recurrent neural networks if time is an important factor in this for these systems, and if not, they could go for the convolutional recurrent neural network instead. They have higher accuracy. Also, the modified callback labeler divergent descriptor achieved the best heuristic performance in the case of the heuristic measure. For classification, we tried different heuristic and also end-to-end models based on spectrogram in the case of the end-to-end, and based on heuristic features in the case of heuristic models. And we tried also different input data, so different classification methods somehow. The first one was based on user-based personal syllable. So each participant would choose the syllable with which they would imitate kick drum, snare drum, another syllable for close hi-hat, another syllable for open hi-hat, etc. So they choose one syllable for each instrument, and each of the participants choose their own. So we let them choose their own freely. And so the user-based, like the first rows, target just, the algorithms target just one participant at a time. So they are tailored, they are trained on only one participant. So they have just a few examples from each of these participants, and they try to model them instead of modeling them as a whole. So classifying just one by one. In the case of the third row, we use these same personal syllables, but the algorithms function in a user-agnostic way. This is not caring about the individualities, the idiosyncrasies of the the idiosyncrasies of the vocal imitation styles of each of the participants. So they take all the sounds as a whole, and they try to classify if this is a kick drum, this is a snare drum, this is a hi-hat, etc. Acknowledging that each of the participants have different ways of imitating these instruments. Then another input data, type of data that we feed the algorithms with, it's 4 syllables, just trying to classify 4 syllables, which are boom, ta, ti, chi, for kick drum, snare drum, close hi-hat, and open hi-hat, respectively. Then we also try to classify the 5 phonemes that we derived from the for the online case, and also beatbox sounds as well. So not only amateur vocal percussion, so also the beatbox sounds as well as we did in the online case. The results, they signal that user-based methods, the 2 first rows, which the first row is the participant-wise calculation of the accuracy, and the second row is the sound-wise calculation of the accuracy. So they are related accuracies to each other because it's the same task. So the user-based methods, so the 2 rows, they perform better than user-agnostic, like significantly better than user-agnostic, which is the 3rd row. We see that classification of the phonemes, like the phonemes that we saw for the online case, which are p, and ch. These 5 phonemes, they also function very, very well in offline, in the offline regime, and achieve the best performance of all the analyzed input data. And beatbox sounds, they are still not as separable as those from amateur vocal percussion, which is the same observation that we derived for offline vocal percussion transcription, for online, sorry, vocal percussion transcription. We also wanted to get these accuracies higher somehow, the user-based accuracies higher, because they usually display low accuracy. The training time in the case of the convolutional neural network, the training time is very high for each of these participants. It takes around 3 minutes. And also there is a considerable risk of overfitting due to the lack of enough data to model. So we tried to, for these reasons, we tried to implement feature learning. So to learn, 32 features from vocal percussion utterances, vocal percussion sounds, and then use the CNN, the convolutional neural network, as a feature extractor, so to avoid overfitting and also get the training time very lower, and with hopes of getting higher accuracy. So the way we achieve this feature learning is that we built a convolutional neural network, and we used the 32 features in the penultimate layer to feed them to a k-nearest neighbors algorithm, so to reproduce the same task as the earliest slides, which were end-to-end. But these features were learned using different tasks in a supervised way, but through different label types. So the first label type was instrument level labels, which were kick drum, snare drum, close hi-hat, open hi-hat. The second level types were syllables, and the third level type were phonemes. These are consonant phoneme and vowel phoneme classified in a multitask learning type of classification, because they were consonant phonemes were classified in a different task as vowel phonemes. And then we have sound labels. So for instance, a label would be the kick drum of the second participant. So all the sounds that refer to the kick drum of the second participant would be a label. Then the kick drum of the fifth participant would be another label. The snare drum of the 11th participant would be another label, etc. So those are sound labels. Apart from those, which are based on feature learning, we compared these results to three baseline algorithms. The first one is a timbral set, which is a heuristic feature set composed of male frequency cepstral coefficients and some envelope descriptors. Then also we have feature selection, which we extracted a bunch of heuristic descriptors and applied random forest importances, so to select among those features. And then we have different type of method, which is the GMM HMM classification engine, which is very used in speech recognition, and it's based, as the name indicates, in Gaussian mixture models and hidden Markov models. And this is user agnostic. This is the only algorithm that is used here in a user agnostic way, meaning that it is trying to classify all the sounds into kick, snare, close hi-hat, and open hi-hat independently of the user. And the results that we have is that CNNs supervised with syllable level ground truth achieve the best and the most stable performances of all. Also, user-based approaches achieved significantly higher accuracies than user-agnostic ones, that is the HMM speech recognition engine. And then we get that the timbral set, full of, which is composed by MFCCs and envelope features, perform better than feature selection, which this indicates that the MFCCs and the envelope features that we chose were quite targeted to vocal percussion, and it's also a very nice set. But this begs the question, did feature learning in the end improve classification results? Because all these experiments were done with the amateur vocal percussion dataset, but also with another one. So we have to repeat the experiments, but only for amateur vocal percussion dataset, as we did in the earlier slides that we wanted to improve. So did feature learning improve classification results? The answer is no, it didn't. It got similar results, which is actually better than the way that we started, because we started with algorithms that took too long to train, like 3 minutes, and also were suspected of overfitting data. So if we have similar results with this approach, this means that we got rid of those problems. Now the algorithms, now the CNNs are feature extractors, and hence the generalizability of this, and also the inference time, it's improved somehow. So it didn't improve accuracy, but it improved inference time and also generalizability. And finally, we get to drum sample retrieval by vocal imitation, which is about retrieving drum samples that are similar sounding than that vocal imitation, so that we could retrieve drum samples from large databases of drum samples just using our voice, so to get similar sounding drum samples. Firstly, we conducted a preliminary data analysis. So the data set was 30 drum sounds and 30 vocal imitations performed by 14 imitators. And we wanted to see how well three different timbral features correlated the acoustic space of drum samples with that of their vocal imitations. So so ideally, these features, if a feature correlates both acoustic spaces, it means that imitators relied on that feature when imitating the drum sample, and therefore the feature is good. The final systems would be better off using these features than others because they correlate both acoustic spaces better. The three timbral features that we explored were the spectral centroid, it has to do with the ratio of lower and higher frequencies of the spectrum of the sounds. Also the log attack time, which is the time that it takes from the onset to the maximum amplitude point of the sound, and also the derivative after maximum, that is the slope from that maximum point of the sound to the lowest. So it's the slope of the decay to the lowest to when the sound finishes, basically. And in order to measure the correlation, we did the Mantel test, which has an associated score. So the higher the score, the more correlated it is at a certain descriptor, and also a p-value, as I say, associated with each score. So the p-value would determine the statistical significance of the correlation measure, so the score. And the second goal was to check if there were some interpersonal differences in vocal imitation styles among these 14 imitators. So they imitated in different styles. And we found that the interpersonal differences were significant, as we will see in the next slide. And also, we found that the spectral centroid was very well correlated. The log attack time was not correlated, meaning that a system based solely on the log attack time will fail because it doesn't correlate both acoustic spaces that well. And also, we found a great correlation to the derivative after maximum of the envelope. So it's the slope of the decay of the envelope. After this, we tried with other descriptors, so the loudness, the pitch, the centroid as well, and also some male frequency cepstral coefficients, and the duration as well, the duration of the sound. And we found that the duration, along with the derivative after maximum as the spectral centroid, as we saw in the earlier slide, were very correlated. They did a good job correlating the acoustic space of drum sounds with that of vocal imitations. And also, we found that the mean MFCCs, particularly the first and second MFCCs, also contributed to correlate these two acoustic spaces. Finally, we also found out that the derivative of the MFCCs, like the dynamics of the MFCCs, are more important than the static measure of the MFCCs, like the mean of the MFCCs. And these signals, like all in all, these findings signal that a good frequency resolution and good time resolution to see the dynamics of each sound would be better for algorithms to take as input. So spectrograms with high time resolution and high frequency resolution would overall be good drum sample retrieval by vocalization systems. And for this, we studied conditional autoencoder models. So conditional autoencoder models would learn information from drum sounds and from vocal percussion sounds. So they would model these sounds, but in a conditional way, in a conditioned way. So we tried 3 different types of conditioning for these autoencoders. The first one is based on sound labels. So whether the sounds are real or so real drum sounds, or but on the counterpart, they are imitations. So 2 classes there. So we condition the output of these autoencoders of every sample that was fed into the autoencoders was given the class, it was conditioned on the class of whether it's real or it's an imitation. Then another label types that we use to condition autoencoders were drum labels. So whether it's a kick drum, snare drum, close hi-hat, or open hi-hat, irrespectively of whether it's real or an imitation. And then we got the 2 together. So for instance, here we could condition on a real kick drum and imitation of a kick drum, an imitation of a snare drum, a real close hi-hat, etc. So 8 classes in the end. So in the end, it would be 2 classes, 4 classes, and 8 classes of conditioning. And we evaluated the results using 4 metrics. The 2 first ones were the mean reciprocal rank and the Mantel significant scores. So these 2 were, they are based on acoustic measurements. So they relate the acoustic space of drum sounds and vocal imitations acoustically. Whereas the other metrics, which are the regression accuracy and the archaic information criterion, they are based on perceptual metrics. So they are based on perceptual measurements. So the data set that we used to calculate these metrics was a data set based on listeners' similarity scores. So several listeners would give a score, a similarity score between a certain drum sound with a certain vocal imitation, for instance. And so this had a perceptual attribute to them. In the end, the results was the new unsupervised convolutional autoencoder improved the baseline that was achieved in literature in the past. So we got several adjustments to the original architecture of this baseline convolutional autoencoder model, and ours improved the accuracy in all the metrics here of the baseline. Then we found that the model, like the autoencoder, conditioned on sound labels and drum labels on both at the same time, performed best or near best in all metrics compared to the other algorithms. And therefore, these both sound and drum type labels, they both provide useful information for feature learning in a drum sample retrieval by vocalization context. So we recommend the use of this type of conditioning when approaching these tasks or similar ones somehow. Lastly, we got the same plot as we did for the heuristic features, but now with the learned features from this autoencoder conditioned on sound labels and drum labels. And these features don't have an immediate acoustic interpretation. These are hard to interpret, but in general, we say that they display high Mantel scores and also low p-values, and also that, as we saw with the heuristic plot, we can compare them here. So as we saw, different imitators imitated different descriptors with different ranges of accuracy. So some imitators relied on some descriptors and other imitators relied on others. So this signals that maybe a user-based algorithm, some user-based algorithms would improve scores even more. And in general, we see that learned features display higher Mantel scores and lower p-values than heuristic features, which means that they correlate both acoustic spaces in a better way. So they are more indicated to perform drum sample retrieval by vocal imitation more than heuristic descriptors. And finally, we will share some perspectives about this PhD project, basically summarizing the findings, proposing future work directions, and also summarizing the contributions of this project. Usually we got high detection and classification accuracies. Also, we improved the retrieval accuracies of user-agnostic drum sample retrieval by vocal imitation. And but we have two ways of improvement here. We have to search for new methods for user-based vocal percussion classification, which is low at the moment. Not even with feature learning we could bring up, although we reduced the inference time and also improved the generalizability of the algorithms by reducing overfitting. But still, these results would be highly improved with other strategies, maybe. We have to improve the online onset detection accuracies as well, which at the moment are mid to high, so around 90% accuracy, but this means that that 10% of the onsets would not be classified somehow, so would not be detected. So this is something that we have to work on for accurate real-time transcription. Also, we have to record a large drum imitation dataset, so to train data-driven algorithms that are based on metric learning, as previous approaches have demonstrated that this technique of metric learning via Siamese convolutional neural networks or triplet convolutional neural networks, these strategies, they work best for drum sample retrieval by vocalization, or just sample retrieval by vocalization in this case. And it will be very beneficial for the task in the future. Lastly, our contribution so far is 1 vocal percussion dataset, 2 open source repositories, and 5 peer reviews publications, which will be 7 in the end, by the end of this PhD, plus 1 journal publication, hopefully. Thank you very much for your attention. I hope you like this presentation, and yeah, see you.